This video is going to show you all of the day-to-day coding skills you need to use JITX to create designs. You'll learn how to sketch out your design using code so that you and your team can stay organized and collaborate. Learn how to add components from our online database of several million parts. How to find and use circuits from libraries, as well as learning how to model components from scratch using EEPROM as an example. We'll make a reusable circuit for that EEPROM using nets, ports, and bundles, and we'll also learn how to automate the supply chain with parametric parts like capacitors. It's not easy to read code out of a video, so there's a written accompaniment to this tutorial and a repository of all the created code linked in the description below. We're starting from the project set up in the last video. Let's take a look at the block diagram. Each of these top-level blocks is going to be its own circuit. In this video, we'll build the EEPROM, the debug interface, and a USB connector. Let's start making the design. We're going to make our code match the diagram, so let's take my design and we're going to rename this to be top level. And so there's a helpful thing, which is select the next occurrence. Now I've selected both my designs and it becomes top level. And the shortcut for that on my machine is Control-D. So saving this and running it, nothing will change because we've just renamed that top level design. And next we're going to add a PCB module for the communications core. This subcircuit can't be blank, so let's add our first part. Open the sidebar and click on Find Components. And we're going to search for the MMSZ 4689 T1G zener diode. Open the detailed view and then click on the Copy to Clipboard button. Now in the communications core, we'll say inst, which is short for instantiate, zener, and then paste the text that was copied from the component search. This is going to pull the part model from the database. If you wanted to make a local version of this to customize, you would click the Create Component button instead. So in the top level design, let's clear out the starting code and we'll instantiate the communications core. Now if we save this and run it with Control-Enter, we can see that the part was added to the board and the schematic. If you select it and press E, you can see the properties. Its instance name is core.zener, so that's the zener device inside the communications core. We could, for example, add another diode to the communications core, save and rerun it. And now we have two diodes inside the communications core. And if we wanted to, we could have 3 copies of the communications core, and we'll get 3 copies of all the circuitry that's inside there. And you can see in the schematic, we have groups for the 3 copies of the communications core, and each one has those 2 diodes. And that's how circuits work in JITX. You build them up in separate PCB modules, and then combine those into designs. And let's clean this up. Next, let's use a predefined circuit from a public library. The awesome JITX repository is a collection of helpful libraries to help you get designs together faster and to reference as examples for doing your own libraries. If I search this for USB, we can see that we have USB connectors in the connectors repository. Let's learn how to install and use these libraries. The installation instructions are at the top, so we're going to copy this line, and in slm.toml, we'll paste it to add that library to our project. Save this, and next we'll pull in the circuit that we want to use. So we want a USB to high-speed interface, which is here mapped to a USB-C connector. So here we copy this line of code, and in our communications core, we can add it. So whenever we change the SLM file, we need to kill this terminal, which you can do with the button there, and press Control-Enter to rerun the design. You can see that it is now pulling in the connectors library, as well as any other libraries that connectors library depends on, like diodes. Now you can see the circuit that we added has a USB connector, along with ESD protection, configuration resistors, and a shield termination. Being able to reuse parametric circuits like this is one of the big productivity boosts. These aren't just static schematic blocks, it's much more powerful than that. And we'll really see that when we get to the power section of this tutorial. Let's use the net statement in JITX to connect the diode to the USB power rail. Net makes connections. In these parentheses, we add the pins that we want to connect. So let's learn how to find pin names. In JITX, all design elements like modules and components and ports are organized in a tree structure. And you can visualize this tree by going to the terminal and running the command view design explorer. Looking at our design tree in the design explorer, at the top level, we have our main module. Inside there, we have the instantiation of the communications core, named core. And inside that, we have our USB interface and our zener component. And we can see that the zener component has the two pins A and K. To access elements in this tree, we use the dot operator. So since we're inside the communications core for this net, we'll say zener dot the name of the pin that we want to connect. So if we write the line zener.a and zener.k, save this and run it, we'll create a net across the two pins of the zener diode. There we go, and here you can press L to turn on visibility of net labels on the board. This is not a useful net per se, so let's make our intended net to USB power. To do that, we're going to learn about two more critical concepts, which are ports and bundles. The pins on this zener diode are actually its ports here. And similarly, this USB interface has ports. If we check the documentation, we can see that the USB interface has ports USB, which is USB data, and VDD USB, which is power. Ports are the electrical interface to submodules, and you would use ports to attach this USB circuit to other things. Ports can be single pins, but most often they are bundles, which are collections of pins. And in this case, they are bundles. You can have simple bundles like the ones in this USB circuit, which is a diff pair for USB data with pins in and P, or a power bundle with pins V plus and V minus. Or for a different circuit, you could have a single bundle that holds all of the pins for a GDDR7 interface. Common bundles, like power and USB data, are defined in the standard library, which you can search from the sidebar. So if we search power, we can find the docs for power, which call out the pins V plus and V minus. So to make the intended net, we're going to change this to USB interface dot VDD USB, which is the name of the power bundle, dot V minus, which is the V minus pin of the power bundle. We can duplicate this down and then connect the positive bundle to K. Save this and rerun it. We now have the intended net across the power interface from the USB component. We're going to add the controller to the communications core. And if we run that, we get an error because we haven't defined the controller. Let's define it now. The controller is going to be reasonably large with the EEPROM, FTDI interface, and the microcontroller. So let's make a dedicated file for the controller. In setting up this file, we'll show you how to create, organize, and link local libraries in JITX. Save main.stanza in a source folder, and we'll call it controller.stanza. JITX finds code by looking for packages in files. So we're going to rename this package Ethernet IO/controller, and we will say, going to import all of JSL. We'll clear out all of the other code that we're not going to use. rename this PCB module to be controller and make it public so that other files can reference this controller. Now, it can't be blank, so let's give it a name and save it. Now, to link local files, we need to edit the stanza.proj file. So here I'm going to add a line that will help it find everything we define in the source folder. Now in main.stanza, say import Ethernet IO/controller, and our code runs without issue. Nothing was added, so let's change that by adding the USB to JTAG debug interface and the EEPROM. We'll repeat some steps. Go to awesome JITX, find the FTDI library. We'll install it by copying this line into our slm.toml file. Save that. Kill the terminal because we'll need a fresh one. And we'll add the application circuit for the FT2232 to the controller module. This device has many options. It's very flexible. So dual channels that each support UART, JTAG, SPI, or I2C, or parallel interfaces. There are also configurable power and speed settings. Traditionally, you'd be reading the datasheet, figuring out your operational mode, and then adding resistors and strapping pins to achieve the configuration. Instead of that, this parametric circuit just lets you specify all that as options. So at a high level, we're going to set our communication modes for channels A and B, and the circuit is going to be configured automatically. And this is what programmatic reuse looks like. You get a higher level function where the lower level details are just figured out for you. Ideally, you only have to look at the datasheet while building the circuit, and then you can reuse it forever. So let's copy this line into controller.stanza. Get that indentation right. Save it and rerun it. Now let's wire up the power and USB interface using ports. As we mentioned previously, ports are the electrical interface to modules. So we need 3 ports on the controller, a port named rail 3v3, which is power. We'll duplicate this. We need a rail VDD USB, which is also power. And we need a USB port, which is USB data. And now we need to connect that interface to the FTDI chip. So again, we'll use net. And let's check our ports on the documentation with VDD 3v3, VDD USB, and USB. So we're going to attach to those. So we'll say debug interface dot VDD 3v3 attaches to rail 3v3. And notice that I have just put 2 bundles into a net. They're both identical, they're both power. And when you do that, all of the connections inside those bundles will be made automatically. In this case, V plus to V plus and V minus to V minus. And that works for any size bundle. So there's our connection to VDD USB. And we need one more for USB. Saving this. Next, we need to add the nets to the communications core module. So we'll say control.USB connects to USB interface. And similarly for VDD USB. Save that and rerun it. And we should see the connections form between the USB connector circuit and the FTDI circuit using that public interface of a module port. Okay, there's our USB interface and power is connected as well. We've seen how to block out a design with modules, how to add parts from the database, how to add parametric circuits from libraries, and wire up interfaces using ports and nets. Now let's complete our learning of basic JITX coding by building a component model and circuit from scratch. We still need to add the EEPROM to the controller circuit and wire it to the FTDI. Our part is the 93LC46CT from Microchip, and there's a link to the datasheet in the description. To make a new component, open the JITX sidebar and press the Create Component button. Let's make a new folder inside Source for components. Now we're prompted for a name. Let's call it the MC93LC46CT. And JITX has created a file for us with a basic template for a component. The Create Component button also adds an entry to the stanza.proj file as well. So it's looking for this package in this file. So if you changed either of these, you'd have to update the stanza.proj file so that your new component model would still be found. Now, it's running this code to generate a preview symbol and land pattern. Zoom to fit. There's our symbol and land pattern. Let's dig into this file to understand how design data works in JITX. Down. In JITX, your whole design is code. Your library is code, your symbols are code, your land patterns are code. This file starts with a package definition, imports the basic libraries including JSL, which has utilities for creating components. Then comes the component definition. A component is a part that you would put on the board. It has sourcing information. This pin properties table defines ports, maps them to a land pattern, and provides information to automatically generate a box symbol. These lines here generate a box symbol and assign it to the pins, and these lines generate a land pattern and assign it to the same pins. Finally, a power bundle is given as an example of structured assignment. We can delete that. So if we change a pin name and change the number of pins on the package, save this file, and Control-Enter to run it, we'll see that we have a new land pattern with 10 pins and a pin named new name here. We're going to finish the detailed model for this EEPROM component. We could reference a datasheet and type this out by hand, but instead we're going to upload the datasheet to an AI model and have it write this code for us. Copy the pin list and manufacturer information, and let's open up our favorite AI model and give it some simple instructions. Okay, now it's generated some code for us. We'll copy paste what we want, save it, and rerun it, and have our AI generated code model. And I obviously want to cross-reference this against the datasheet. So we'll verify that our SOIC package has the same pin map, and it does. And we'll also want to verify that the packaging dimensions are correct. This looks like a standard SOIC, with the exception that, we have 8 pins and not 10. So save that and rerun it, and we have our AI-generated code model. Obviously, you can get the AI to do a lot more than extract a simple pin map. I don't really like this symbol layout from the default template, so let's adjust the order and direction of the pins in the symbol. So make DO left, ESS left, right. And we'll move this selection, move line up. All right, save that and rerun it. And we have a customized symbol as well. Copy the package name, and then add the EEPROM to the controller by saying inst EEPROM, paste the package name / component, which is the device that we just defined. Save that, and then rerun the design. There we are. Now we have our custom EEPROM component added to the controller subcircuit. Oh, and there's one last thing. Delete this view line. because if we don't, it'll get a visualization of that component every time it's used in a design. To hook it up, let's wrap it in its own subcircuit. Create a PCB module. It will be public. We'll name it module. We'll instantiate the EEPROM component. And next we need to add some ports. So we have port VDD 3v3, which is power. We have a port CFG, which is microwire 4. And next we need to map these ports to the circuitry inside the module. So we'll say net EEPROM dot, let's just start from the top, CS CFG dot. Let's check the pins for that microwire bundle. Microwire 4. Microwire 4 has pins clock CS D0 or DO DI. Okay. CS to or do CLK. Next we'll have VDD 3v3, just power V plus VCC. Okay, so a little repetitive, but it's actually a really big advantage to be able to put custom circuitry inside a subcircuit and then wrap it with standardized bundles like power and microwire. You get a lot of reuse and ability to swap out this circuit for something else later. To finish this circuit, we need a pull-up resistor for the ORG pin and a bypass capacitor. To add those, we'll show one last way of adding parts, and that's to use parametric functions to automate your supply chain. We're going to call out what parameters are important, and then use automation to choose parts automatically. And this is what has been used to generate the vast majority of the resistors and capacitors in this design. So we'll import JITX/parts, and we'll use the insert resistor function to add a pull-up resistor. And this takes arguments. The first two arguments are the pins you want to connect. RG. Next, you want to give it the method you use to choose a resistor, and that's in the helpers function. And then finally, you just need the value. Resistance is 10 kiloohms. And similarly, we'll use insert capacitor to add a bypass capacitor. Pins VCC, VSS. We'll use the arguments and helpers to choose capacitors. Capacitance is 2.2 microfarads. And we'll add argument short trace. To finish off, change the component to the module to capture the subcircuit we just made, and then connect the ports. Net to the debug interface .cfg port. Save that and run the design. So here's our subcircuit, and with that, you've learned how to make custom components and circuits from scratch. This training covered all of the basic coding practices you need to use JITX. We learned how to sketch out a design using code, so you and your team can stay organized and collaborate, how to add components from our online database of several million parts, how to find and use circuits from libraries, how to model components from scratch, using that EEPROM as an example, and then how to make a reusable circuit for that EEPROM using nets, ports, and bundles. And finally, we also covered how to automate the selection of parts using the pull-up resistor and the bypass capacitor as examples. We now have our USB, the debug interface, and its configuration EEPROM, which is a good amount of circuitry. In the next video, we're going to show how to customize the schematic for this design that we've created.